Hi, in this example, I want to take a look at static equilibrium. Now, static equilibrium is when the sum of the forces is equal to zero, the sum of the torques is equal to zero, and the object happens to be at rest. And the example we're going to look at is something that would be familiar if, like me, you watched a lot of 70s early morning cartoons. So an adventurous bear decides to try and go after a picnic basket that's been placed at the end of a beam that's supported by a cable. Now the cable's making an angle of 50 degrees with the beam, but that cable can only withstand 800 newtons of force. And the bear is already 1.2 meters down the 4-meter length of that beam. So if this weren't a cartoon, would the bear already be safe? And what we'll look at in a follow-up is to see if the bear is actually going to be able to succeed given the details that we have in this problem. So, as I said, static equilibrium, some of the forces, some of the torques, and those are vectors. We need to take a look in every direction. But in physics, typically what we do at this level is we'll just look at forces that happen to be in the XY plane, the plane of the board. So all of our torque will just be around a Z-axis. So to do this, we'll draw an extended free body diagram. So of the forces that I've talked about, the bear has a weight. The bear is standing on the beam, so at that distance x away from the end of the beam will feel a normal force from the bear. Because remember, the weight pulls on the bear, pulling him into the beam, so the beam pushes up on the bear, and by Newton's third law, the bear pushes down on the beam. The beam feels its own weight, and that beam, we're told, has a weight of 240 newtons. Now at the end of the beam, we have that cable that's at an angle of 50 degrees from the beam, and we know that we're limited to a force of 800 newtons. On the other end of the beam, there's a hanging basket. The basket weighs 60 newtons, but again, that weight affects the basket itself. So it has to be connected to the beam somehow, so technically there'd be a tension ultimately from the basket pulling down on that beam, so that force of tension would be the same as the weight of the basket. The weight of the bear would be equal to the weight of the normal force as long as this beam happens to be parallel to the ground, which is what our picture says. So, is that enough in order to keep this from moving? Well, we have forces that are up, forces that are down, but this force is also pushing to the left, or pulling to the left, if you will. So that means we need something that's at least pushing it to the right. We have a hinge. That hinge has to be doing something. So if it's pushing to the right, I'm also assuming it probably has to be pushing up, because from experience, that's what hinges would do on trapdoors. Now, if we want to find the forces, like we did back when we talked about Newton's law the first time, some of the forces in the x direction, in the positive x, we have the force of the hinge in the x direction. We don't know that. Minus the x component of the tension. In the wire, we don't know that either. We're stuck. Can't use that until we find one of those two forces. In the y direction, we have more forces, but we still have the same problem. Two unknowns. There's a y component to our hinge force. That's presumably upward. There's a y component to our tension. That's presumably upward. We could stop here saying two unknown forces, but just for completeness, we have the normal force from the bear, 500 newtons down, the weight of the beam, 240 newtons down, and the tension created by the basket, another 60 newtons down. So if we had a different problem where this cable happened to be exactly where it would need to be to balance everything out, then we'd be okay, because there would be exactly 800 newtons of down force, 800 newtons of up force, but it would be a juggling act. And if the bear moved or the basket moved, all bets would be off. So, taking a look at this problem, there's one more set of equations to look at. Sum of the torques. Now, the really cool thing about static equilibrium is if the torque sums to zero around one axis, the torque sums to zero around every axis. So, let's pick the point where we don't know the forces, the hinge. So, if that's my center, the sum of the torques at that point is zero. There's no distance. The torque from the bear is just going to be equal to the distance x for the bear times that normal force, and that's in the clockwise or negative direction. For the beam, it's at half the length of the beam times the weight of the beam, negative direction, clockwise. For the basket, it's at the far end, so its distance would be the length of the beam, the normal force from that basket, clockwise, negative direction. So we have this tension in the wire giving us a counterclockwise torque, and that's happening at the end of the beam, so its distance would be L, but we need to know the sine of the angle between the beam and the wire, which would be the sine of 50 degrees. So if I set this equal to 0 and solve for the tension in the wire would be my distance x, the location of the bear, divided by the length of the beam, times the normal force from the bear, 1.2 meters over 4 times 500 newtons, means I'd have 150 newtons there. I'd have half the weight of the beam, or 120 newtons, and I would have 60 newtons, the force from the basket. And then I would have to divide by the sine of my angle, and the sine of 50 degrees is 0.77. So if I take that 333 newtons, divide by the sine of 50 degrees, that means that wire has to have 431 newtons of tension to keep the bear in static equilibrium. So, applying Newton's second law to these pieces, the upward force from the hinge would have to be 470 newtons, and the x component from that hinge would have to be 277 newtons in the positive x direction. In part 2, we'll take a look at whether or not the bear would be able to succeed in getting all the way to the picnic basket. Thanks for watching.